Hey everybody, welcome back to Young Engineers of Today. I hope you had a good weekend. I hope you're ready to continue with model rockets, because that's what we're going to do. We're going to do more model rocket stuff. So, well, first off, how was everybody's weekend? Anybody do anything interesting? Let me not get ahead of myself here. I feel like it's always good to see if anybody has any interesting stories from the weekend. Still waiting on your motherboard. I'm sorry to hear that. You got second at OM Regionals. What's OM? Odysseyofthemind.com. Okay. Huh, that's pretty cool. Creative problem-solving competition. Nice. Well, congratulations. Oh, so this is a very engineering-based problem too. Creating a robotic pet. Not so haunted pop-up house and rubber band-powered devices. That's pretty cool. Well, congratulations. Oh, last year's? Okay, gotcha. Yeah, usually they give you a sample of last year's 2017 problem synopses. Family that brings home an Autobot instead of being performed to program tasks. Wow. Nice. That's pretty awesome. Well, there you go. For those of you who are interested in creative problem solving, you've also got Odyssey of the Mind. Um, all right, so model rocketry. Now, last Wednesday, we spent a fair amount of time talking about fins. In fact, a lot of time talking about fins. Uh, so much time, in fact, that you guys are probably sick of talking about fins. But we'll spend some time talking about them again, just as a review. We'll go over what we went over last Wednesday, and then we'll get started on motors. Now, motors is going to be a little bit more physics heavy. I sort of included some basics of equations and stuff like that. Here, I did the same thing for motors. There's just some more of it, but let's spend some time going through this. So yeah, like fins are the main stabilizers on the rocket. We already knew that. They stabilize the rocket's trajectory as it launches. Um, they make sure that the rocket just flies at least mostly upwards. But structure of the fins is actually pretty important. So the reason why it's important is because there's drag. Drag is the thing that exists. As long as there's an atmosphere and as long as we've got moving things, there will always be drag. Drag is just the force of the air basically pressing against the rocket as the rocket is moving. In essence, you can think of it like friction, air friction, kind of. It comes in two forms. You've got induced drag and profile drag. Induced drag is just drag that exists whenever the rocket uses its fins in order to correct its movement. But most of the time, model rockets, at least smaller model rockets, do very well at flying straight up. Like, you don't have to really worry about them going all over the place. So induced drag tends to be pretty low. But that's the whole point of a fin anyway, is a fin is meant to correct a rocket's path, keep it from straying. And whenever something like that happens, induced drag increases. Now, profile drag just is always there. It comes from the shape of the fin. Um, and it's always present as long as the rocket is moving and as long as there's atmosphere. So, that's just something to keep in mind. You also, you want to, you want to have at least some amount of induced drag because you want the fins to be able to correct the rocket's path in case it ever, starts to try and do weird stuff. But you want to minimize profile drag because that's always going to be there, and all that does is just waste speed and fuel on your rocket. So for that reason, you want to spend some time considering different fin designs. Now, in order to talk about fin designs, we talked about Reynolds numbers. A Reynolds number is just a number that helps describe how turbulent a fluid-like air is. And remember the whole thing about gases and liquids are fluids. Fluid in a physics sense is something that moves fluidly, so isn't a solid. So for that reason, a gas is considered a fluid. And then in this picture here, let me go back down. In this picture here, it's a candle. This is the air moving upwards from the candle. As you can see, it starts out a very laminate movement, smooth movements, and then it becomes turbulent up here, or bumpy and chaotic. So we talked a little bit about that too, mostly just define the terms. And we mentioned that we wanted to basically make sure that the fins that the rocket uses are able to take advantage of that laminate air, because a lot of the air coming down the sides of the rockets is very turbulent, because the nose cone on the rocket pushes the air out of the way, which creates a fair amount of turbulence. So we want the fins to be large enough in order to basically grab onto that laminate air and keep the rocket steady. However, that does bring up the fact that the larger the fins get, the more profile drag you have. So that brings us back to designing the shape of the fins. And we spent some time talking about that. In essence, in our example here, we sort of talked about it and but I mentioned that probably the fourth one here, the rectangular one, is one of your best bets because it has a consistent performance at lower Reynolds numbers, that is to say more turbulent air. And on top of that, the surface area is the same all the way across, so it's able to, unlike this one, you would have to make it much larger in order for it to, hit that laminate air, those higher Reynolds numbers, which would increase the profile drag, because if just like this part of the fin, let me do a different color, just this part of the fin is in the laminate air, as you can see, it's not nearly as much surface area as this part of the fin over here. So you kind of lose some efficiency. Now, granted, this will have a lower amount of profile drag than a rectangular fin will. But on the other hand, a rectangular fin, as you can see here, I kind of colored in that surface area on the elliptical fin. On this one, you can see how much more surface area there is. That's how much more control these fins have. In addition, because of the fact that they work better at lower Reynolds numbers, that is areas over here, the rectangular nature of the fin allows it to perform better, even though it's going to have a higher amount of profile drag. So that's just something to take into consideration. Same with the diagonal one. Anyway, so yeah, that's what we spent Wednesday talking about, was fins, which sounds a lot less exciting when I put it like that. Today, we're going to spend time talking about motors. Motors could potentially be more interesting. Who knows? I could bring so much math into this that talking about something cool like gunpowder motors becomes less interesting to you. Though maybe you still find it interesting, in which case, perfect, awesome. You think rocketry is still cool in that case. In which case, maybe you could look more into aerospace or something like that. But anyway, motors. So first of all, it might be important to understand exactly how motors work from a physics perspective. I mean, we do know that, okay, so there's some fuel inside, and the fuel is ignited, and then it sends out thrust, like you've got in the picture here. This is the actual propellant burning in a model rocket motor. And so from that perspective, that makes perfect sense. Fuel light up, fuel burn, make thrust, rocket go fast. So far, so good, right? Except, like, how does it actually do that? Well, you have Newton's third law to thank for that. For every action, there is an equal and opposite reaction, because the thrust from a motor is assuming that it's actually like mounted onto a rocket on a launch pad and not sideways like it is here. The thrust from a motor applies a downward force. It shoots downwards. Now, that would be the action in this case, that downward force from the motor. But for every action, there is an equal and opposite reaction. The opposite reaction in this case is the rocket moving upwards. So you've got the action, which is the motor thrusting downwards, and the reaction, which is the entire rocket moving upwards. Just in a very simplified sense, that's exactly what's happening. I mean, in a literal sense too. I mean, that's exactly what happened. Is what happening. What is happening? Blah. There's an equation for this, in a sense. Like there's an equation that can help represent what exactly is going on here. As you can see, you've got force of gas is equal to force of rocket, and this is where we start getting into the physicsy stuff. Force of gas is equal to force of rocket. That's what the F represents. Now the M represents mass and the A represents acceleration. As you can see, we've got two equations here which are actually essentially the same thing. Because let's spend a little time talking about this. Now, here's the deal. When we're talking about physics, a lot of times we use metric units because metric units tend to sort of reduce and work together with one another very well because they were built that way. A degree Celsius is, well, 1/100th of a gradient between frozen water and boiling water. Let's see here. A milliliter is 1 centimeter cubed area of water or some liquid. I believe a joule is how much it takes to raise 1 milliliter of water by 1 degree Celsius. There are a lot of ways that the units are sort of interchangeable with one another. They interact with one another, and so for that reason, physics is great for that kind of stuff. So, for that, with that in mind, when we talk about mass times acceleration, we talk about mass in kilograms and acceleration in meters per second squared, which is weird, right? What is that? Well, that can be expanded to meters per second per second. Oh, wait, no. Yes. So let's think of it this way. All right, so what does meters per second look like to you? Insofar as like, what do you think that represents? This might be a bit of a simplistic question, and it might be so simple that it's throwing you guys for a loop. Well, okay, how about this? Yeah, well, it's how many meters something goes in a second. It's speed, right? You guys know it as, probably more often as miles per hour. But miles per hour can also be represented like this. Miles per hour. Meters per second. It's a unit of speed. Now, meters per second can be thought of like this. Meters per second per second. That is to say, how much the speed is changing in a given second. That's all that is. That's what acceleration is. It's just how quickly speed is changing. So we've got kilograms, mass, and meters per second squared, acceleration. We mash them together. And we get kilogram meters per second squared, which is force. Which is kind of weird, right? But basically all this is saying is force is a measure of how quickly it can accelerate a given mass. So take a ball of paper on your desk and you blow on it, and the paper moves a little bit, right? You know, for a moment there, it's accelerating. Paper doesn't weigh that much, and you don't really make it go too terribly fast. So even though your breath is exerting a force upon that piece of paper, that piece of balled up paper, it's probably not a whole lot of force. Press down the gas in a car. Car weighs a lot, and depending upon the car, it could start going pretty dang fast. You know, it could start accelerating greatly. That is a fair amount of force. And that's just a sort of a different, that gets into a little bit more explanation, but like for now, just think of it like this. Force, the size of a force can be affected by two things. It can be affected by how big or how massive. It can also be kind of thought of as how heavy, but that can be affected by gravity. But like how, which is in and of itself a force, so it's better to think of it in terms of mass. How big something is, that's the first thing that can affect the size of the force. And the second thing is how quickly you are making it accelerate. How basically the magnitude or the size of that acceleration. So for that reason, we want to take into account both when we're trying to figure out, you know, how much force is being exerted upon the rocket. Now back to this here. The force of a gas is equal to the force of the rocket. What do we mean by what do we mean here by gas? Well, the gas is simply just the gas that's exiting from the back of the rocket. The gas that is being moved by the engine going off. So that can have, I mean, as we all know, gas has a mass. It exists. It's not a vacuum, so therefore it has a mass. You know, providing any sort of weird physics wizardry. It's a lot more than you might think, too. I think on any given day we have something like 2 tons of atmospheric pressure on us, which is just the weight of the air. Which, you know, we've evolved to be able to withstand that. So we don't even think about it. That feels like normal to us. But like, you know, you dive into a pool, you can feel the water kind of pressing in on you, especially as you go further down into the water. You can feel the water sort of pressing at you from all angles. That is essentially you're feeling the mass of the water. So just like diving into a swimming pool, the air around you also has a mass. So we take the mass of that air, or in this case gas, because we want to be you know, as generic as possible, times the acceleration of that gas, how fast it's moving. And that will be exactly equal to the mass of the rocket times the acceleration of the rocket. Now here's the wacky thing. You know, obviously our rocket isn't going to be as light as air. So they have to equal each other. Well, let's take a look at this a little bit. So let's say, given how much the air weighs, or not how much the air weighs, given how much air there is, the back of the rocket is moving, and how fast it's moving, it's equal to 150 newtons of force. That's what this represents. Force, this unit right here, kilogram meters per second squared, is also known as newtons, thanks to Sir Isaac Newton, who basically wrote down this equation. It's actually Newton's first law, force is equal to mass times acceleration. So since he was kind of the guy who came up with this whole thing, or at least codified it in a way that we can use it in math, we named the unit after him. Or maybe he named the unit after himself. Anyway, newtons is the unit, kilogram meters per second squared. So let's say between the weight of, or between the amount of air and how fast it's moving, we get about 150 newtons of force. Now, since these must be equal to each other, that means that this on this side is 150. So this on this side must also be 150. It just has to be, because they're equal reactions, right? Opposite just simply means that it's going in a different direction, but they're still equal reactions. They have an equal amount of force. So that means the mass of the rocket times its acceleration must equal 150 newtons. Since force, let's just say this, force is mass times acceleration, that means that we have to take both the mass of the rocket and the acceleration of the rocket into account. So if the rocket's mass is 2 kilograms, which is 4.4 pounds, I believe it's about 4.5 pounds, not quite 5 pounds. If the rocket's mass is 2 kilograms, well, 150 newtons of the air moving divided by, well, so that the air moving is 150 newtons, which means that the rocket moving, the force on the rocket must also be 150 newtons. If it's mass times acceleration, all we do is we try and get the mass out of the equation, which will leave us with acceleration. So we divide our force by the mass, again, to bring it out of the equation. So 150 newtons divided by 2 kilograms gives us 75 meters per second squared. So that means that the rocket is accelerating at a rate of 75 meters a second. It's going really, really fast. It's 167 miles per hour per second. As I say, it's going 167 miles per hour faster per second. The first second, it's moving 167 miles an hour. Second, it's moving, what, 334 miles an hour. The third, you get the idea. Now, because the beauty of this is it's a very, very simple equation that just works very well. So if the rocket is heavier, it's going slower at the same rate. So if the rocket is 5 kilograms, that is to say 2.5 times heavier, it's accelerating at a rate of 30 meters a second squared, which is 2.5 times slower. If it's 10 kilograms, which is twice as heavy as 5 kilograms, it's accelerating at a rate of 15 meters a second squared, which is half the speed it would be accelerating, or half the rate it would be accelerating at 5 kilograms. So using mathematics, we can actually figure out the force that is going to be exerted on a rocket, and we can figure out from there how fast our rocket should probably move with a given engine inside of it, as long as we know how much air that engine is moving, how quickly and how much of it. So this is another thing to keep in mind. The mass of the rocket includes the mass of the motor used to make it go up. So as I've said, before, slapping a bigger motor onto a rocket isn't always the best solution, because sometimes adding more fuel will make a problem, the problem being, having enough fuel to get into space, worse. Because as you add more fuel, you increase the mass, which means that it's accelerating more slowly, and sometimes that's ideal. Sometimes you want it to accelerate more slowly because lower down in the atmosphere, like we were saying last Monday, lower down in the atmosphere, the air is thinner, so, or excuse me, the air is thicker, so there's more drag, which means that you want to be accelerating more slowly anyway, because otherwise you're just wasting fuel. So, you can have more fuel, kill two birds with one stone because the rocket is accelerating more slowly. So it's not wasting as much fuel, and then it has more fuel once it gets to the point where there's a thinner atmosphere. But again, that's to a certain point. At some point, it becomes actually more unwieldy to add more fuel. You start going slower than your your maximum recommended speed for the density of air and stuff like that. This is all stuff that aerospace engineers have to worry about. Granted, working with a model rocket, you guys aren't really going to have to worry about that kind of stuff. But if you ever decide to continue with that train of, schooling or whatever, and go into that kind of career, then you'll have to think about that. You'll have to wonder that kind of stuff when you're with a crack team designing rockets to go into space or whatever. So just think back to this moment where I kind of sort of stumbled over my words and mumbled to you something about the fact that adding more fuel isn't always the solution, and go, I got it. We should have less fuel. And, you save the day. Because that's how these things go. Anyway, it's not always the solution to have a bigger motor, but a lot of times it is. Sometimes you really do need a bigger motor, and for that reason, they come in many different classes and sizes, as you can see here. You've got some really small ones, and you got some pretty big ones. And these aren't even, this isn't even the full range of like types of model rocket motors available. They come a lot larger too, and we'll get into that in a second. But they I say, how do we read these here? Basically, what I mean by that is each sort of model rocket motor comes with its own classification. And how do we read the classifications that that help describe, how much thrust it puts out, and for how long and stuff like that. So motor designations come in 3 parts, which give you just about all of the information you need to know about it. Now, there's also this single stage part over here, which just basically means that, it's meant to really only be used on its own, but whatever. Anyway, no, it doesn't have an ejection charge. That's what that means. So, for example, in this picture over here to the right, this is a picture of the side of a motor with the designation C6-3. So let's take a look at what all that means. So the first part, which is the letter, the C, it denotes the total impulse. The total impulse, broadly speaking, is the overall power of an engine. So letters can range from A and B and C and so on, all the way up to O, which is a lot. And the reason why it's a lot is because each letter grade represents double the overall power. That is to say, a B-class motor is twice as powerful as an A-class motor, but it's only half as powerful as a C-class motor. A D-class motor is twice as powerful as a C-class, an E-class is twice as powerful as a D-class, so on and so forth. So when you get up to O-class, those are some really powerful motors. This is actually a picture of high-power model rocketry, as you might imagine. It's a big rocket, but it's still not like, something designed by NASA or something like that. But it's a big, big rocket. Anything above class G, so that is to say H and higher, is considered high power model rocketry. I'm not sure exactly what class the rocket motor is in this picture, but I'm going to guess somewhere in the vicinity of O class. So it could be an M or an N, could be an O class. I don't think it's the largest it can go, but regardless, it's a big motor. When you're talking about this right here is a C class. A C class, so an A class is, let me find a picture for comparison. Trying to find a picture of a smaller model rocket motor next to like somebody's hand or something like that. Okay, so this is a very low resolution picture, but this is about the size ratio of an A-class model rocket engine to a human hand. This right here is probably a B class, this is a C class, this is an E class. Unknown what this one is because it's not showing, but I would guess like a G. I would guess about an F or a G class, probably a G class. So this right here is still larger than this right here. So that hopefully gives you some imagination room to try and figure out how big these things all are. Now, granted, of course, you've got the ruler down here as well. So this motor right here is about an inch thick. As to say, its diameter is about an inch. So, that you don't really have to imagine. You can also get an idea there. But whatever, it's sometimes everybody needs different metrics to compare size off of, and sometimes having something to relate to, like the size of a human hand or something like that, can also be helpful. But anyway, O class is pretty powerful, especially considering the fact that H class is considered high power model rocketry, and O class is what? Let's see here. I, J, K, L, M, N, O. 8, 16, 32, 64. It's 128 times more powerful than an H class. It puts out thrust equivalent to 128 H-class engines all running at the same, or motors all running at the same time. That's crazy. In fact, these rockets are powerful enough that you need permission from the FAA to launch anything at that size. So, yeah, I mean, I know I've mentioned that before, but think about that for a second. You need permission from the government to launch these rockets. A, to make sure that there aren't anything flying in the sky, and B, because sometimes these rockets are large enough to be picked up and they fly high enough to be picked up on defense radar or just radar in general, which freaks the FAA out, which can freak the Air Force out, and everybody has a bad time. So you want to make sure that they also know that you're launching something like that, so that you can not scramble some emergency air defense. Now, granted, that's probably not going to happen, but there will be some people who have for a moment, a very high heart rate while that's happening. So anyway, the number directly after the letter, in this case A10 or B6 or D12, represents the average thrust, or how much power it puts out at any given moment versus how long it puts out its power. Weird, right? So basically, we've got the overall power of an engine, which is the letter. So you can think of it like, I guess, how explosive. Like, let's think of it in terms of a car. So the letter represents how large the gas tank is and how potent the fuel mixture is, both together. In a sense. So the higher the letter, the larger the gas tank, and the more potent the fuel mixture. Now, when we're talking about average thrust, how much power it puts out at any given moment versus how long it puts out its power, This is sort of like, now you've got your gas tank and you've got how potent the fuel is inside of it. How fast are you driving that car? Because if you drive faster, you use fuel more quickly, right? If you drive slower, you use less fuel. Your car tends to be more efficient with the fuel that it's using. And a lot of that has to do with drag and stuff like that too. But basically, the higher the number, the more thrust that an engine will put out at any given moment. However, the shorter the burn time. So a B6 is going to burn, decently hot, and for a short period of time. A D12 is going to burn very, very hot, but for a very short period of time. Like a B2 would burn very slowly, but also wouldn't put out that much thrust. Now keep in mind, at these sizes, you've got the same amount of fuel essentially in there. You've got the same amount of like gunpowder, whatever you're using. And it's still just gunpowder, but regardless, you can, based on how you pack it, you can either have it burn more quickly or more slowly. And if it burns more quickly, it's going to burn more of it at the same time, which means it's going to put out more power. You get the idea. So the higher the number, the more of the fuel it burns at any given moment. However, because of that, the shorter it burns. So, you can always sort of combine these types of things. So you can, if you decide to continue with model rocketry, certainly. You can always combine the motors. So you can always have like a high average impulse to get your rocket off the ground and moving fast. And then once it's up in the air, you can use lower impulse or lower average impulse numbers like 6, 5, 4, stuff like that to keep it moving upwards and for a longer period of time. So yeah, for that reason, it's kind of good to sort of know how these all work together. If you want a rocket that is very light, but you want it to go up higher, you might want to use a lower impulse number. If you've got a heavy rocket, but you want it to go like really, really fast, you can use a higher impulse number. Just keep in mind, it's not going to really burn for as long and potentially not go as high than a lower impulse number. Well, so yeah, now what about that final number? So the final number, this one's really easy. So this is just after the dash. But the final number represents how long there is, how long a delay there is I am putting typos all over the place. Before the ejection charge blows. And this is just, usually, it's just straight up in seconds. And it's just pretty straightforward. So in A10-3, once it's done burning all of its propellant, it's going to have a delay charge of 3 seconds. B6-4, once it's burned all its propellant, it's going to have a delay charge of 4 seconds. A D12-5, once it's burned all its propellant, it's going to have a delay charge of 5 seconds. Pretty straightforward, right? So at the very least, that last number can be pretty easy to determine. Now the other two, the B6, the D12, the A10, I've been talking about, thrust and impulse and all that kind of stuff. That can be a little bit more nebulous because it's kind of like, well, how much is a 10 more than a 6? And there are ways to determine that. There are, unsurprisingly, mathematical equations for that. But that's the kind of stuff that we're not really going to worry about too much at the moment. That's the kind of stuff that you can take a look at when we start using like the Open Rocket simulator software. Yeah, this way you can predict how long your rocket will spend coasting before blowing the ejection charge and beginning recovery. Tense agreement. So with these three things, you can kind of get an idea of how big a motor is that you might want for your rocket. But we've been talking about impulse. But what does that actually mean? So you remember I was talking about force and all that stuff? Um, impulse is the amount of force in seconds. So how much force an engine will impart upon a rocket or whatever by igniting it versus how long it burns for, or just the amount over time, that kind of thing. So impulse is basically how many seconds it takes to accelerate a mass a given amount. It's a little bit different from that. It's not exactly that. Um, I guess it's sort of like the overall amount of force exerted over the amount of time that it exerts that force, kind of. Anyway, it has to do with things like integrals and stuff like that, which is a little bit beyond the scope of what we're looking to talk to you guys about for the purposes of picking a model rocket motor. There are people out there who teach calculus a lot better than I do, and they'll at least be able to introduce you to integrals and stuff like that, and then you can use that information in order to get a better idea of how impulse relates to what you're looking for. But in order to get a better idea of what kind of motor you might want for your rocket, you generally want to figure out how much your rocket will weigh versus how fast you might want it to go. And I say weigh just because if you know how much your rocket weighs, you can get an idea of how much mass it has, where you can figure out how much mass it has. But I do want to stress that mass and weight aren't necessarily the same thing. A lot of times the terms are used interchangeably, but mass is how much stuff there is. Weight is how much it, weighs, which is strange to say, but think of it like this. You stand here on Earth. You weigh a certain amount, right? You go to the moon. You weigh a different amount. You go to Mars. You weigh a third amount, somewhere in between the moon and Earth. But you've not actually lost any mass, right? You've not gotten any smaller or larger, anything like that. You yourself have not changed. It's just your location has. And more importantly, the amount of gravity that is being exerted upon you as a person. So weight is mass times gravity. Now here's the thing. Gravity is an acceleration, in essence. Gravity is a measurement of sort of how in an area with no atmosphere or something like that. So assuming no other weird sort of things to wrenches in the equation in order to mess things up. It's a measurement of how quickly something accelerates generally towards the object that's exerting the gravity, always towards the object that's exerting the gravity. But it's a gravity here on Earth is a measure of how quickly everything accelerates towards the Earth. Gravity on the moon is a measure of how quickly everything accelerates towards the moon, so on and so forth. So you have a mass, you have an acceleration, so weight is a force. That's just a funny little aside. But anyway, so that does it for motors and for today. On Wednesday, we're going to spend time talking about different types of recovery systems and what might work best for you. This one's a little bit less, you don't have to generally agonize over the decision as much, but it's good to know what kind of options you might have. So that's what we're going to spend Wednesday going over. Hopefully that should be interesting as well. Um, and then next week we're going to continue with model rocketry. We're going to get into probably a whole mess of other stuff, and determining how high your rocket goes and stuff like that. But anyway, that is going to do it for today. So if you have any questions about anything, I'm here. I'm going to ask the poll questions, and then we'll leave it open for question and answer time. Otherwise, once we're done with once we're done with the poll questions and you don't have any questions for me, you're more than welcome to head out. Have a wonderful couple of days, and we'll see you on Wednesday.